All right, good evening, everybody. So I'm Don Miller. Been, as I was saying, an amateur astronomer for most of my life. I'm a volunteer with NASA. I'm a NASA Solar System Ambassador, and hence my beautiful little badge and shirt. And basically what we do is we're advocates for NASA's research and studying space and topics related to space. So whether it be life in the universe or how we protect the planet from asteroids. I have topics that I can discuss like crazy. It's fun. I really enjoy it. I'm a retired person. I was a researcher at Pfizer's facility in Collegeville. All right, so let's get started. So today my talk's about life beyond the Earth and NASA's efforts to try to elucidate that. And it's not just NASA, but I'm going to be closely focused on that. I like to start with this one. If you haven't heard this story, I think some of you seem like you're very big advocates of space, so you probably know this one. This is back in 1990. A guy named Carl Sagan was a hero of mine. He had this very poetic story about the pale blue dot. This is in February of 1990. Voyager had just gone beyond the orbit of Neptune, looked back into the inner solar system, and took this photograph. These are raster lines, so don't pay attention to those because it was not the greatest technology at the time. That little blue dot is us. And so it's right there, okay? And so he was more poetic than I would be, but if you have a chance just to read that a second, it's very humbling to sort of put ourselves into perspective. So it's a lot on one little dot, right? So every science that man has, there's a lot of great unsolved mysteries that we're trying to solve. And some of the questions are, what's most of the universe made of? We know it's not made of the matter that we're made of or what our planet's made of. And we use the term dark matter and dark energy to describe that. And yet we haven't found any of that yet other than through the impact of what it's doing to the universe. What came before the Big Bang? We have literally no idea. You could say maybe, is it cyclical? Was there anything? We don't know.
Yeah, I think there is.
It could be. Are we alone in the universe? And that's really what I'm going to address today. It's one of the great unanswered questions of mankind, not just of physics or astronomy. And so many more. So I'm not going to try to address everyone. So certainly some questions to consider here. There are some basic questions, like what is life? So if you're looking for life, you better understand what it is that defines life, so you know if you found it. Okay? What are the ingredients for life? What supports life? So could we find some signals that would allow us to see that? What makes a place habitable? What places on Earth are like places beyond the Earth, so that we could actually use those as basically surrogates to study how would we analyze those to see if we could find signals for life. What conditions can life tolerate? Meaning life on Earth, okay? And those are extreme. What are the potentially habitable places in our solar system, either now or in the past? And how do we search for this beyond the solar system? So topics we're talking about, I'll do a very brief primer on astrobiology, okay? And I'll tell you why I'm going to do that in a second. Then review the efforts in our solar system, past, ongoing, and what's going to come. And review the efforts beyond our solar system as well, okay? Each one of those topics could take hours, okay? We're just going to go real fast through all this stuff. If you have questions, ask me as I go along, and just realize I've got a lot of slides, so if we do a lot of talk, we won't get to all the slides. So it's a balancing act. Okay, so why discuss astrobiology? My favorite thing about astrobiology, it's the only science I know that doesn't have a subject, yet. Okay? We've never found a life beyond the Earth. So we have no subject for that science. So why discuss it? Well, questions are, how does life begin and evolve? The more we understand how that is, the more likely that we can know if we can find it. Does life exist elsewhere in the universe? And what are the future of life on Earth and beyond? We know our planet wasn't always like it is today. Planets evolve. Humankind and species evolve. So things are always changing. The more we understand that, the more we'll understand not only other life forms maybe on other planets or solar systems, but also our own. Challenge regarding the second Genesis. What is life and how will we know when we see it? And this was, could you please move on? You're ruining my rock picture. So life begins, there are many definitions of what's consensus for life, how do you define it? Life begins the first semi-permeable membrane. That was one definition. Another is life begins the first self-sustaining metabolic cycle. Okay. Oops. RNA-like, so you need to encode life so you can pass down benefits from generation to generation and future generations. Begin a self-replicating mineral that could actually start it well before what we would traditionally call life. And it goes on and on. I would recommend, if you're interested, Google this. It's just amazing how much is out there as far as detail about, you know, what people are thinking about the definition of life. And it's just no one true definition. Common characteristics of life on our planet, the only life we know, are common biochemistry. Everything that's alive today has DNA and RNA. Ordered structure, reproduction. But there's things that are alive that don't necessarily reproduce. Growth and development, reaching maturity. Energy utilization. So basically, we have to take in food of some type, okay? Response to the environment. So actively sensitive to respond to external stimuli. Homeostasis, meaning maintaining your body warmth. And then evolutionary adaptation. Okay? That's what we know from Earth. And if you're looking for a really interesting read, Astrobiology Primer 2, it's online. Really good, that thick, and but it's really fascinating. Working definition that actually NASA's been using since '94 is self-sustaining chemical system capable of Darwinian evolution. Alternatively, maybe have a genetic system that evolves through change that accumulate during the organism's lifetime. So this is actually called Lamarckian evolution, for those of you who remember your biology. Darwinian is normally what we think of, where you're basically passing it down from generation to generation, but some people argue for Lamarckian evolution within a lifetime. So, the solar system. When you think about the solar system, what's it made of? Well, it's mostly what the universe is made of, hydrogen, helium, and a little bit of what astronomers call metals. To an astronomer, a metal is anything with an atomic number above 2. Okay, so anything beyond helium is a metal. It's not what we would traditionally consider a metal, but it's what astronomy looks at as metal. And if you look at the metal composition, it's almost predominantly oxygen, carbon, and then you start getting into the other things here that make up this planet, ourselves, and are important things for life. So how does life emerge from this crazy mix of elements? No one knows for sure, but the one theory is, you know, basically primordial Earth, and it starts making nucleobases, carbohydrates, amino acids, carboxylic acid, and these sort of things take a long time to work. They've become nucleotides, small proteins, ultimately going into the protein world. Membranes develop, and then they start replicating and ultimately get to a protein or RNA, DNA, and life as we know it. Now, this process isn't fast. This process on our planet took billions of years. Okay, so, and that's important for us to understand, because when we're looking at other planets, we have to understand how much time did they have to produce life, as we understand it. Okay, so if they didn't have enough time to get to really sophisticated, like pick up the phone and say hello, okay, then you might be looking for a little microorganism. They may not have had enough time to get beyond it. This is just some thermo, if you remember your thermodynamics. Basically, my point here is that organisms need energy. And they need an energy environment where they can have, like chocolate, where they have lots of energy that they can actually metabolize and do this using, if you remember again, your thermodynamics, your Gibbs free energy, that basically it's a spontaneous reaction. You don't have to use energy to actually get energy. That's basically it. Common solvent for life on Earth is water. Without water, we wouldn't be here. Okay, other planets, alternatives have been proposed, such as ammonia, sulfuric acid, methane, ethane, you name it. There's been lots of things discussed for solvents that could work. The water is so nice because of its polarity. It can solubilize a lot of these things that I said or make up the Earth, and yet they will let it go too. Carbon versus silicon-based life. If you've watched any science fiction movies, there's always something about what about a silicon-based life form. The thing is, you know, carbon can bond to 4 atoms at a time. And those bonds are strong, but not too strong. What makes carbon so fascinating is not that only it can bond to 4 things, but that it actually will let those go. So bonds typically at temperature will allow reactions to occur. If you look at silicon-based life, the silicon-oxygen bond is really strong. It is really tough to break. So it's probably not going to work, at least in a water-based environment. Now, if you're going to say it's in some other type of media, that may be the case. And if you're old enough to remember the original Star Trek, this is Kirk going against the silicon-based life form. All right, good place to start searching for life beyond the Earth is in the solar system. Okay. Let's start, well, we could start with Mercury. Who wants to start looking for life on Mercury? No, okay. All right. What about Venus? The answer is, yeah. Look for life, maybe not today, but maybe it existed in the past. Okay? Today, it's a runaway greenhouse. And it's sort of, I have a whole nother talk on Venus because it's a fascinating planet, because it wasn't always the way it is today. And why did Venus take the road less traveled by, or maybe more traveled by, and become basically a greenhouse monster where you got the surface is melting lead, the atmospheric pressure is way above Earth's atmospheric pressure, and you know, it just doesn't look very hospitable, as my little cartoon here sort of shows. But it wasn't always that way. From the samples we have from landers and probes that have gone around Venus, basically the belief is it had an ocean, and that the ocean basically boiled away at some point in the past. Can we find signs of that previous life on the planet? It's going to be really hard with basically a molten surface. Any signs of life that were there are going to be hard. But maybe in the upper clouds. Maybe there's, because if we get up high enough, the temperature gradient's pretty severe. And so you can get up to regions in the clouds where the pressure is more modest and the temperatures are more reasonable. Venus might host life. A few years ago, you might remember the phosphine story. This is a natural product on Earth. It's produced on Earth either abiotically by the planet itself, by volcanic release or acid-base reactions, or it can be done through biotic processes. And the reason I bring that up is that in 2020, there was a spectroscopic analysis of the Venus atmosphere that basically said, well, there's phosphine in the atmosphere, upper atmosphere, but the levels seem way too high for natural production. So it must be that maybe there's life on the upper atmosphere of Venus. Unfortunately, a subsequent analysis showed that they had calibrated wrong, and so that basically the phosphine levels are much lower and in line with what you would expect from natural environment. They create quite a ruckus for a while. But people were still going, probes, not only NASA, but the Japanese and European space agencies are sending probes to try to evaluate further and putting in actually balloons that go down and float in the upper atmosphere of Venus to try to understand what the composition is and what's there. Plan future missions to Venus. I think India has one later this year. NASA has 2. Actually, they just delayed this one by 4 years. So unfortunately, that's going to be a little bit later. It's going to probably come right in time for the ESA mission and Vision, which is disappointing. And it's due to money, budget. Goals: understand how the planet evolved to what it is today. Did it have water for sure, and how did it lose it? The geology, and can it help us understand how planets change? Both our planet, but also planets that we're looking at with the Hubble or with James Webb, to understand how those planets might be evolving that we're looking at out there. Mars. You know, Mars is a favorite one to talk about for life. I wish on my telescope I could see it that well. No evidence yet for life on the surface. Okay, we've been looking now for over a decade. Planet likely to have been very different as well in the past. So this goes back in time. There was speculation since the 1850s on life on Mars. Burroughs wrote his books. You got the War of the Worlds. A lot of great science fiction books came out about Martians coming to Earth and being super advanced. Then people actually started looking through scopes, and the thing with our human eye is we're used to seeing patterns. And so when we're looking for things, we can see patterns sometimes where there aren't really patterns. And so they were seeing all these canals on the surface of Mars. But as we've used spacecraft now, there are no canals on the surface of Mars. There are some dust, sand dunes, and they do shift, but it's not like this. Today, Mars, it's a cold desert. Beautiful picture here. This is from our Curiosity rover. Just to give you an idea, on Earth here, our hottest temperature is 136 degrees Fahrenheit approximately. On Mars, it's about 86. Coldest, minus 126 on our planet, 284 on Mars. With the average temperature on Earth being basically just above freezing at 14 degrees, and Mars being down below freezing at minus 81 degrees Fahrenheit. So very different planets today than what we may have been in the past. These are just some other facts about it. So Earth, our atmosphere is 78% nitrogen, 21% oxygen, 1% other things. This is 96% carbon dioxide, and then noble gases, and some other things. But look at this. This is Death Valley on Earth, on top, versus the Gale Crater on Mars. They look very similar. So there are features on our planet that mimic what we see on Mars. Mars yesterday was warmer and wetter. We think it had a reasonable atmosphere. It had water. These are giant, what we think or believe are outflow channels from the Mars Odyssey probe that was circulating around the planet. So we think about 3.6 billion years ago, it might have looked like that. That's just a rendition. We don't think it had as much water as Earth does, but it had water. And it probably was in what we call the habitable zone. So it had some time to potentially be a place where life could begin. So with that in mind, look at this. This is using what we know. How did life go? Well, starting from here on Earth is the only life data we have. The prokaryocytes, these are basically organisms that don't have a nucleus. Okay, very simple life forms. So they formed very quickly. Somewhere, Earth, sun ignites, Earth forms, the moon strike happens here, and then within basically a few 100 million years, once the planet cooled down, you actually had life started. So you say, what happens fast? So it must be everywhere. Well, not necessarily. It happens fast, but then look how long it took from there to all these different species to get to dinosaurs and ultimately to man down here. So what I alluded to before, life evolution takes billions of years to get more and more complicated. So you're not going to get to fish and vertebrates that you would very quickly. Which means if what we're looking for, say on Mars right now, if we were to find fossils that look like these, it'd be game over. We'd be saying, great, found life. But Mars didn't have enough time to generate that level of complexity. All we're going to hope for on Mars is something like with their smatolites, which I'm showing here. This is from the Earth. These are microbial biosignatures. They lay out in mats. We have them still on our planet today. And we have them about 3.6 billion years old in Australia. Okay, so these actually lay out like this. So if we found structures like this, that would be a very strong signal that life did exist on the planet.
How can you differentiate that from just another type of rock in that?
You can also look at the radioisotopes.
Okay.
It's a structure plus the radioisotope mix, because life will then bring in oxygen, start utilizing oxygen. And these things were actually producing oxygen, so they were using CO2 and producing oxygen, but they can also use the radioisotopes of carbon, which some of whom are long enough that you could actually try to look at. So that's how you do it. And this is what it looks like today in Shark Bay in Australia. So that could have been in the early oceans on Mars. Curiosity rover, it's been there since 2012. Taken lots of pictures and samples. A lot of good chemistry has been done. Found chemical and mineral evidence of past habitable environments. Okay, continues to explore the rock record. So we don't have a signal yet for microbial life, but it keeps looking. Perseverance rover and its little buddy here, Ingenuity. You know, pretty amazing helicopter. It was only supposed to make 5 flights, and it just keeps on going.
It's moving.
It's moving, yeah.
Yeah, but is that a real photo? Is it
It's a photo. It's a GIF I'm using. Okay.
How is it doing that? As I hold is it have one of
Oh,
those
it has. See this
extenders
here.
on its
This is
iPhone?
the arm. It's doing a selfie.
A selfie, yeah.
It does selfies all the time. It actually has its own blog going. It sends blogs. It's pretty fun. Yeah, it's sort of, you know, anthropomorphizing the machine, but it's fun. And, you know, this has been so successful for us that the next Mars will actually make larger versions of that and probably carry several of them so that they can go around. The hope is that what this is doing is collecting samples right now. It's doing some analysis, but it can't do a lot of analysis, so it's collecting samples and putting them away that for a few years we're going to launch a ship to take and pick it up and bring them back. If this thing can't do it for us, because it's hopeful that that can actually motor over to wherever the ship comes in a few years, hand off the samples, and it lifts off. If it's broken, the new rovers, or sorry, new helicopters will actually pick up those samples and bring them back.
Oh, wow.
And this is actually where it is right now in the Jezero crater. And here's the delta. You can see the inlet valley here. So when you look at Earth and inlet valleys, are one of the most fertile places on our planet for life. So the point was to go here because if we had signs of life, we think this would be a good spot to find it. This is just showing more of what the crater looks like. You can see how the flow pattern would have been. This is some of the delta that you can actually see from Perseverance itself. And this is what I was just talking about. So basically, around 2027, 2028, we'll launch a ship that will go out to Mars to pick up the samples. They'll return back to here, this planet, in about 10 years time total. China is also trying to beat us to the punch. So good luck. If they can beat us, great. Let's just get the science done.
Are they going to steal our samples?
That's a question. I wouldn't put it past them. They steal everything else, so why wouldn't they steal the sample? So we still have to design this and make it, so it's going to be tight to get this made, but it will be very interesting. So it's going to have an orbiter component, so basically this will launch off, dock with the orbiter will then take the samples, and it launches itself back to Earth. So how about beyond Mars? You know, you think about it, they're gas giants once you go beyond Mars. There's no terrestrial planets. So you're saying, well, there can't be any life on any of those. As far as we know it, no. There's probably no life on actual gas giants. However, these gas giants are so massive compared to us that they have a ton of moons around them. And those moons are actually getting heated up by the tidal forces of these massive planets. So they actually may be a lot warmer than you think, because you think all of these out here, not only are they gaseous, but they're frozen, right? It's really cold out there. But maybe it's not a problem. So moons being considered for exploration. On Saturn system, 2. Enceladus, from the Cassini spacecraft before the 2017 crash, so this is this one here. And then Titan, here. And then Jupiter, Europa, Ganymede, and Callisto are being looked at. Now you say, well, why are you looking at those? You know, how many of these worlds could have life? The question is, are chemical blocks common? Can they inhabit deep water ice if it exists there? And you know, is it common across the solar system? we think we're a planet that you consider us to be like almost an ocean planet. We've got oceans everywhere. But really, the amount of water on Earth is not very much. If you look at the planet as a whole, and you were to take all the water off and make it a ball, its own little ball, this would be the water.
On Earth?
That's it. It's actually rare. Water on Earth, if you take the planet as a whole, not a lot of water.
Seems-
Okay? But if you start looking at some of these moons, and even Pluto, look at Enceladus here. The size of the moon, how much water it has, it's almost all water. And then Europa, all the way out here, look at Ganymede.
Wow.
And these are size appropriate. So you're getting an idea. These are ocean worlds. Okay? And they're not teeny. So Titan, this is the Huygens probe in 2005, and that's actually the image from the surface. The probe visited in 2004, lasted 7 years in orbit. The probe only lasted a short period of time on the surface, really cold, and they got hydrocarbon lakes on the surface, so I assume it was fairly inhospitable to it. I never did find out exactly why it died, but I don't think we know exactly why it died. But it's it's a planet of interest. And if you want to get an idea, Earth, our atmosphere is nitrogen mostly, one atmosphere, as I said, about 298 Kelvin. Titan, also nitrogen, a little more atmosphere than we have, 1.5. But it's only about 95 Kelvin. So remember, absolute zero is 0 K, and that so we're pretty warm compared to that. You say, well, that's really cold. Water freezes at 273. Excuse me. Well, here the liquid cycle is water, and these are compositions. Here it's methane. So on the surface, methane is actually acting as the aqueous phase. But you follow the organics. There are organics in the atmosphere, and we think they're being generated here underneath. Because of the tidal forces that these moons are getting from these massive planets, we have assessed basically the structure of these planets, and we're pretty sure that there is a liquid ocean underneath these a thick ice layer. The question is there life under there, and what would it be composed of? So we think that you can come through different processes that actually could make hydrocarbons down here in the water, which could work their way up through the crust into that atmosphere of 1.5 atmosphere pressure that they currently have. And so this is just another cartoon just sort of showing how this would actually be conversion. Planet is accreted, so you got CO2 under a lot of pressure with water. Your CO2 can go to methane, and that can work its way to the surface. And this is some of what the atmosphere would look like. In the chemistry, people have done models to try to understand how this chemistry could actually work. This is actually a simple model. Okay, there's much more complicated models today. What could be happening to produce all these complicated molecules on the surface? As we would say, if given nature a chance, it finds a way. Okay, so it's going to keep going and finding ways that it could make whatever it can make. This is just giving you an idea of the cutaway here of the moon and showing the surfaces with the ocean here underneath. This is just depth layers showing that we probably have a pretty thick layer of ice on top, and then an area where you're getting mixing and aqueous phase, and this could be slushy or maybe not slushy, and ultimately getting down to the core of the planet where you're going to have solid rock down there. So how would you get in there? Well, we're developing technology to explore it. How do you penetrate? You'd use an ice mole. That is what the term they call it, an ice mole. And basically this is a device that either has a boring on the end or it actually has heating elements or both on it, so that you can actually change not only how it's boring but the temperature of the probe, so that you can tell it if I want to make a turn or I want to go down straight down. So it depends on how you heat it. This is the components of it. It can get quite complicated because also it's more than just boring, it's actually taking samples. The goal is to have it bore down through kilometers of ice to get down into the aqueous phase, collect samples, and look for what we might be finding down there. And so these are some of the examples they did testing this in Greenland, on some of the glaciers in Greenland. NASA they do a lot of this research decades in advance of when they're actually going to use it. So right now we're sending out probes. In the future, we'll be sending out devices or probes that actually land with ice moles that will start digging down through. But we have to develop the technology here first. This just goes to show you what would that mold be looking for. So it might be looking for some of the fatty acids or other components that we would consider to be some of the basis for life. And this is just some of the equipment that they're developing to look at these, and these are showing some of the spectra that you would have to actually compose those samples. What about life beyond the solar system? So I've talked about the solar system. What about beyond? So with that, we're detecting life with telescopes. We're trying to, I should be saying, Hubble, James Webb, and others in the future. Trying to look for biosignatures. I mean, we won't see little green men out there waving at us, okay, they're too far away. But we will be able to say, look for a signature of an atmosphere that would say, hey, you know, that looks like something you might think would be life. James Webb has detected carbon dioxide in the atmosphere of a planet 700 light years away. It's a hot gas giant, so it's probably not likely to have life, but it's just showing the technique that we can actually detect composition of atmospheres. So, good way to assess habitability and whether it's inhabited. A lot of exoplanets we've seen so far are hot Jupiters. Why? Because the technique we use typically is what's called a transit technique. And you really need a large body going in front of the star to actually block enough light that you can actually do that. And so you're going to see predominantly larger planets. Earth-based telescopes and space telescopes, though, will play a huge role in the future. And they use transit spectroscopy, which I'm just talking about, gravitational microlensing. This is going back to Einstein, and he predicted that light around a massive object would be bent. So if you can watch background stars beyond the star you're looking at background stars behind it. If those stars get perturbated, then you've got a heavy body of planet that's coming in front of it. Okay, so we can look for that. Coronagraph is another way where basically you block the central star and you look for those. And we have actually taken pictures of other solar systems and young systems where you can actually see the planets moving around the other systems. Biosignature, if you're going to say, okay, if I'm looking for a biosignature, you better define what you think you might be looking for. It's going to be reliable, meaning is it biotic versus abiotic sources? Survivability. Can planetary sinks be saturated? So, as an example, what I'm saying there is, Earth, when this planet was first formed, had no oxygen. And it took billions of years for those microorganisms to actually be churning the CO2 and producing oxygen as a byproduct, that we're saturating the rocks on this planet with oxygen. So the planet itself is a huge sink. So it takes a long time to saturate that. And on this planet, when that saturation finally happened, we have what was called the Great Oxygen Event. And the oxygen levels shot up very quickly in the atmosphere. Not quite to today's levels. Then there was a second oxygenation event that got to today's levels. So it's got to be that the sinks won't take up all the material. The detectability. Are you actually able to detect it with the instruments you're using? So one molecule you might think of as a biosignature is oxygen. Oxygen is a very reactive molecule. If you put oxygen into a planetary atmosphere without replacing it, it's going to react with something else and it'll be gone. Okay. The reason oxygen is still around us because we've got all these plants that are producing more oxygen. Okay. So it's a good signal on Earth, but only modern Earth, as I was just saying. The beginning Earth would not have had that. So there can be false positives encountered due to things like photolysis of oxygen molecules like water and CO2. So we have to really understand more about what are the best biosignatures to look for. So this is an ongoing research area. I can't say it's definitive at this point at all. This is just an example just showing in our solar system. If you were looking at the spectra of Venus, Mars versus Earth, you would see basically water on Earth and you would see oxygen, okay, which you don't see on the other two very much at all. So that would be kind of definitive for our solar system. This is what I was talking about before with the transit method. So envision this as a star, and what we're looking at is if we happen to be lucky enough that the orbital plane of the planets around that star are right in line with us, so that the planet actually comes in front of the star, then it's blocking the light of that star. So the technique basically is follow the brightness of that star, look for a dip, and see it come back up, and then you actually know what happened there. You can actually get the size of the star, of the planet, and knowing how far away you can start getting the size of the star using some basic physics rules. But also, additionally, if it has an atmosphere, which I'm depicting very large here, then what you can do is take a spectrum, which means you break the light apart for, you know, I don't want to say something you don't know. So basically taking the components of light, breaking them apart, and looking at how bright they are and what's missing in that, because if something has molecules that are absorbing it, those wavelengths will be missing. So take the spectrum of the star without the planet in front of it, then wait for the planet to come in front of it, take the spectrum again, subtract the two, and what you get left is the spectrum of the atmosphere. Because the atmosphere will be absorbing different things than what the star did. And that's how you do it. And this is actually some of the work that was done right here. These again, showing water, carbon dioxide. These are on other stars. Or planets, sorry, exoplanets. So currently, astrobiology missions, Hubble, I will go through them all. Mars Reconnaissance, the Curiosity rover. Test mission has been looking for exoplanets like crazy. Perseverance and James Webb has been extremely successful on astronomy in general, as well as it's starting to do some amazing things with regards to looking at exoplanets. Future, we got the Europa Clipper mission to Europa coming up in about a year or two. It's supposed to arrive around 2030. The timing is always approximate until they say they're really ready to go. Dragonfly mission to Titan, launch in about 4 years, arrive in 34. And then the Grace Telescope, the Roman Grace Telescope, 27. This is actually a nice companion to both the James Webb and to Hubble. You know, it's also an infrared, so just like James Webb is, but it's a very wide field. So it can actually be used to look for signals of systems around other stars, of planets, that we could utilize and look at with, say, the James Webb, which has a much more fine focus. So it's a very good synergistic scope that we can't wait to get up there. This one's an interesting one because it's sort of playing on what the Ingenuity copter did on Mars. So Dragonfly mission, basically, based on 13 years data, it's going to be basically a helicopter. Remember that this moon has a very thick atmosphere. So it can actually be quite a large craft here that can go around and loop around the moon to different areas very easily by flying from one spot to the next. So it's going to be at the equatorial area, which they call the Cendrillon dune fields. And basically it's going to fly, we're thinking at least 100 miles on the surface, maybe more. They always designed the things that they're going to last a lot longer than they do. So finding life beyond the Earth, there's myriads of different things going on that are trying to look at this. It's an exciting time. I think there's hopefully things we're going to find in our own solar system, hopefully, but maybe beyond. And so thank you. I'll take your questions. I went through a lot, so sorry.
What powers the helicopter?
With the helicopter now, it's solar powered.
Solar, okay.
Yeah, which is the problem, because when it gets to Martian night, they had to park it and put it into standby mode. And the problem is the Martian night, as I showed you, goes to like minus 280. They were not sure it was going to come back out, but it did.
Is it a month or is it a night?
Oh, it's a few months.
A few months at night.
And then it basically came out. And it let it charge up, and it started right up again. So it's been amazing.
So,
Yes.
I haven't tried any kind of nuclear fuel. I think that was an issue on Cassini has nuclear power, I think.
Once you get out beyond Mars, there's not enough sunlight. Generally, you're using nuclear power at that point.
They don't want to try it on Mars just because they don't need it.
They don't need it, and it's a safety factor.
Yeah.
So they figure there's enough light there. Why put that type of material on Mars?
And actually, another place where they're actually legitimately exploring life, but on Earth, but not trying to emulate overseas, is in Antarctica. And they were sending tubes down. There's something called Science News that I read.
Sure, I know Science News.
And they're trying to look and say, hey, some of this up there is unexpected in terms of how the biology is.
Yeah, no,
And some of the biology of things at the sea. We don't know a lot
Right.
about what's in our seas.
agreed,
So,
Deep
a lot of
Mariana
variety.
Gulch.
yeah.
Mariana, go down there.
So what do you think? Are we gonna find life out there?
Yes.
Yeah.
No.
Positive?
Yeah.
Okay. So you're pretty sure there's gonna be life in the universe?
Pretty sure, but I'm not
much,
sure
yeah.
we'll spot it in my lifetime.
Yeah.
It may not be
Not a
intelligent,
person,
but it'll be
not a
life.
person, but.
In the whole galaxy, do you
amoebas
think
or
there's gonna
plant
be,
life?
well, what about the whole galaxy?
You mean everything, the whole universe?
Well, just the galaxy, let's just
This
consider our
galaxy, yeah.
Could
Yeah, I
it be
think there's-
possible that it's so different than what we think of as a life that we won't recognize it as life?
That's the concern. That's why astrobiology is so important. We need to understand what the options are that could be alive. So it's not something that, right there and living and we miss it. You know, it's exactly what we're concerned with.
That's what I'm trying to say, if you read even sometimes about the deep sea creatures they found on this planet, there's some pretty exotic stuff,
Yeah.
you know, like around thermal vents and so on, so yeah.
Yeah, there's a whole nother talk I give which gets pretty heavy, but it's really about how you predict the probability of life in the universe. And, you know, there was a famous astronomer, Drake, back in the 1950s. He was a young grad student just coming out and was working at Green Bank and came up with Drake's equation because he was starting to look for little green men, basically. And he wanted to try to keep it on the down low. And he spent a few $1,000s on equipment, but the story got out that he was doing this. He didn't succeed getting any signals from, he looked at 2 close stars. But the whole world got excited about it. Then NASA and the government asked him to, it wasn't NASA at the time, but the equivalent of NASA at the time, asked him to put together a conference on it. And he asked all 12 people who at the time were interested to be part of it. And he came up with this equation to try to predict the probability of extraterrestrial communicating life in the universe.
That we would be able to see it, I think, in our lifetime.
That we might be able to see.
Yeah.
And then, so it was a very simple equation, but very impactful I'll get to you in a minute. And so mankind has been studying this in the 50, 60 years since. And we've learned a lot more about how the universe works and the physics of the universe. So and biology and what's actually permissible zones around stars as well as the galaxy for life. So you can start getting really deep into probabilities and trying to predict these things. But bottom line of that story is, it could be, I'm not sure it was yours, somebody said, we just might not have looked long enough. The estimates that one person did, it was one set of researchers, it would take a few thousand years of looking for us to find a successful signal, because they're just that far apart. It's probably not that many. When you think about what formed our life here, there's a lot of things that happened. You know, if the dinosaurs hadn't died, we wouldn't be here, okay? There'd be some little mammals, but they probably wouldn't be us, okay? So an asteroid had to come down and hit the Earth and wiped out the dinosaurs, okay? So does that happen on every planet? Probably not. The moon struck, a Mars-sized body struck the Earth, making the moon. Without the moon, the Earth would be wobbling, and a lot of times planets wobble and flip. That would not have been hospitable. So that's another low probability event. So you can start adding up these probability events and say, it's really unlikely that if you started over again, that we would be here. Okay? So as a scientist, I have to say, there's no proof that there's life beyond Earth.
Well, if Andromeda is the nearest galaxy, 4 light years away, what's the
4 million.
chance? 4 million light years? 4 million, that's right. But, I mean, what's the chance we can get to there and see what's there?
It's too far. We can't even get to the first closest star.
Which is?
That's Alpha Centauri. That's 4 light years. We don't have it,
So,
our technology.
oh, okay, it's just too far away, but we can catch it in telescopes, can't we?
Oh, yeah, we can see it.
Because if they can see these things that are like 56 million light years away and give us a picture of it, why can't they take a picture of Andromeda?
They
And see
can, they
what's
do.
there?
The problem is, it's so far away, and even if there was somebody there flashing lights saying, we're here, hello, you're talking it's gonna take millions of years for that to reach us.
Oh,
We're,
sure,
we're
it's
limited by the physics of the universe, which is the speed of light.
Yeah.
Only goes what the speed of light goes.
But how do we get pictures of something 56? How, across the universe?
Well, the universe is 14 billion years old, so light's had a lot of time to come to us. Okay, so we're seeing very distant objects
Mhm.
because we've had a lot of time for that light to come to us.
Okay.
Okay?
People don't read anymore, but some of the older highlights when they were talking about emergencies, when you're trying to continually talk, to go back and forth to account for the lag time between Earth, say, and Mars.
I mean, absolutely.
And it's, I read
Even
that
lag
somewhere
times
else.
here when we do missions out in space, like, I don't know, you guys probably all watched the recent DART mission, which was the double asteroid redirection test. Fascinating, whole nother talk on it. But basically, we were trying to hit this little object millions of miles from Earth with an object traveling at 4 miles per second, and want to hit it right in the center. And it was so far away that signals from here to there took 36 seconds at the speed of light. So we had to develop the probe to actually be autonomous, and actually had to find its way there, because if it waited for us to tell it what to do, it'd be past it. Would have totally missed it. And it hit it dead on. It was an amazing success. So if you want to hear about protecting our planet, talk to that guy about having me come back. Okay. All right, anything else, folks?
So where do UFOs or UAPs, whatever they're calling them these days, fit into this?
Yeah.
You know, I mean, I'm just giving my opinion, so it's not NASA's opinion, just so for the recording. But, you know, what I've read about the programs and what's been recently coming out, you can go through almost all of those unexplained, and they're pretty explainable as light phenomena, people not familiar with the objects they're looking at, etc. There are a handful that aren't explained, but then it's usually the data that's the issue. It's very fuzzy data. You don't really know if they really saw what they think they saw. So there's been no real proof. And I mean, face it, folks, we don't have the technology just to get even to the closest star. So if some species is able, smart enough to come all the way here, we're ants, you know, as far as they're concerned. They have nothing to hide. They can come and land onto the Capitol lawn and do whatever they wanted, okay? We wouldn't be able to stop them. So, you know, they don't need to hide. So this whole thing is just, it's fascinating, but I think it's science fiction, my opinion. You know, I just think you gotta be realistic. I mean, we don't have anything like that. Maybe in 100 years, or not even 100, 500 years, 1,000 years, we might have the technology to get to some of these other things. But we could envision things where you could, you know, using ion drives and stuff, where you could get to a fair fraction, a few percent of the speed of light, and then get to another close star, and maybe we'll start seeing some things. But whether there's anything at Alpha Centauri, probably not.
There
But
was,
then the next one's further away, so go ahead.
there was a talk a couple years ago about the light sail. They're
Yep.
developing a thing that uses a sail and somehow photons from the sun. Is it still out there, or?
Oh yeah, I mean, the light sails is a fascinating idea because that's free energy. If you can capture the light energy that's coming from a star, or if you're a super civilization, way beyond us, and you have massive lasers that you could fire at that thing, you could get it going really fast from just the light energy, because photons have momentum, okay? Don't have mass, but they have momentum, okay? And that momentum gets transferred to the sail, okay? But you need a material that can spread out uniformly in a controlled way, that the thing's not going to start spinning in space. It's going to be huge, the light sails. I mean, there was just a recent test of that idea by the, blanking on who did the test.
Planetary Society?
Planetary Society, thank you. You know, their data was a little fuzzy, so I don't really know that they proved the point, but that was a nice try, you know. And so we still haven't had definitive proof of light sails yet, but the material's the challenge.
Well, they're still developing and it's not an actual thing yet.
Nobody's developed one
Oh, okay,
definitively.
it's still a theory.
Yeah.
I think they're
Well,
working on
I think
it.
people are working on it, if that's what you're asking. But it's not that, I'm just saying, they haven't put it into practice. No one's used a light sail to travel to like the other planet. That's part of one of our challenges, like, you saw how many years these space programs take. So, you know, just to get back, get out to Titan, you know, and back, you're talking 10 years. And why so long? Because we have such limited energy, you know, chemical reactions just produce only so much energy. So we need better energy sources so we can start traveling faster and getting to things, especially if we want to go beyond the solar system. So what we do with these in our source, we end up using swing-bys other planets. So we might go into Venus, swoop by because we're going out to Saturn, but we'll go past Mars, and we just use the gravity well, so planet by planet, to slingshot it further and further out. So it's a fun, you know, dynamics game that would be great mathematics, but it's slow.
We can't even get the train from Phoenixville.
No, what can you say? Yeah. Getting a high-speed train in America, you know, when will that happen?
From Washington,
Put a light
D.C.
sail
to
on
Boston
it.
anymore
Yeah,
by
put a light
highway.
sail on it. So,
Because 95.
so what do you thought? Is this on topic? Was it too high, too low?
Way over my
It was
head.
too fast, but I liked it.
Okay, all right. I'm always looking for feedback. Good? Okay,
Yeah.
great.
So how did you become a NASA ambassador, solar system?
I've always been interested in astronomy, as I was saying, and actually when I was in college, I was torn between becoming an astronomer or going into engineering. And so I went into chemical engineering because I'm a pragmatic guy, and I think, how much money can I make as an astronomer? You know? So I kept astronomy as a hobby. So it's been a fun hobby, but I've always missed it. The idea of space, and I've been, you know, always thinking about it. So when I retired, I said, well, I heard about somebody else being a NASA ambassador. I'm like, whoa, what are we talking about that? So then you have to apply, you have to submit, you know, basically why you would be a good ambassador, references, etc. And you know, they try to geographically locate us around the country. So that's how ultimately they accepted me, and it's been off in the races since that time. So,
Well, thank you for coming, Don.
thank you. Good audience, thank you so much.
Thank you.